Hi, this is Iklak Sidhu. Welcome. This is the second part of the module on the topic of prediction within the DataX course. In this module, we're going to extend the topic of linear prediction from the case of two variables, which was basically one input variable and one output variable, to multiple inputs and multiple outputs. Okay, in the last section, we talked about having one input and one output. So you have basically a system or a formula inside it. You put in an X, and with a formula, you get a predicted value, Y. So this time, let's take a look at a couple different examples, two cases. One is, suppose you have one input like X, but instead of just one output, we want to have multiple outputs, like Y1, Y2, Y3. So this case, it's actually not a problem at all. What you can do is you can have three different formulas inside this system. So you put in X and you use, say, G1 to give you a Y1, you use a second formula to give you Y2, and you use a third formula to give you Y3. So there, you can have multiple outputs that way. The second case, it's a little more complicated. And this is, what if you put in multiple inputs, not just one X, but X1, X2, X3, all as inputs. And now you want one or more outputs. And what we're going to do is we're going to talk about what can you do, what can be done to handle this case. So to do this, first of all, what we're talking about is we're saying that we're going to have an X as an input. We're going into a predictor formula, and we're going to have Y. The X is the way to think about this is that the X this time is in a structure that's a table, or more specifically in a matrix. And what we're looking at is that you've got a row of that table, like say 1, 3, 4, 6, 2, that row is being provided as an input into this predictor formula, and you're going to have one or more outputs, and that will correspond to one row in a matrix, which is Y. And if you have one output, then there's only one column in that matrix of Y. It's a vector. If you have two outputs, or let's say three outputs, like in this picture, then there will be three different columns, and that row, the corresponding row from the X, will give you that corresponding output row here with three different values, three columns in Y. Now, this is the basic machine learning framework that we're using in this course and that we want to explain. So we're going to start with the idea that there's a table of data. And in this case, every row is like a different person in your table or in your database. And some of this data, you also know something about what it is you want to predict. So you have a column of outputs which are labeled or marked or already known. And then you have other data for people where you don't actually know the answer. And the basic idea is that you want to use the top of this table in order to learn something so that you can make predictions on rows that are below, that is on the data that is out of sample data. So what happens is that you take this data, the input part, and we're going to basically put that into the matrix of X. So whatever was a text value, for example, like married or their job occupation, either we're going to convert that into numbers, like categories or something like that, or we're going to throw those columns out. We're not going to use them. And so that part becomes X. Again, it's n rows deep, and D is the number of columns, the number of features or dimensions that there are. And in terms of the output, in this case, we're talking about prediction. So there's some predicted value that we'd like to have. So it might be like a credit score, in which case we would have a column of all the different credit scores that we already know. And the basic idea here is that X is chosen from some distribution. We don't actually know this distribution, but if we had this data that's in this form X, and it was chosen from that distribution, that there would be a function, we don't know this function, but there is a function that if you put X into that function, you would get that value of Y. So now let me show you the same thing, except we'll do it with a simple example, and we'll illustrate the idea of prediction, or specifically in this case, linear regression. And what we have here is a table. It has 4 rows in it. For example, the names of each person is a different row. And also on each row are 3 characteristics: their age, how many years they've worked for a certain employer, and their current income. And then there's also a column Y here, which is the credit score that they currently have. And so what we're going to do is put that into the format that we talked about before, where X is the input, and it has exactly these same numbers from the matrix in it. There's a W, which we don't know, but we need to calculate. And there's Y, which we already do know because it was in sample data, and we do know what the credit scores for these particular people are. And the basic idea is that if you know, or if you can calculate what the best W is, calculate W to give us the best predictor, then we should be able to take any future row in X, multiply it by that W, and get a predicted value for Y. The one other thing which is worth understanding on this example is that we've added an extra column of 1s. And this extra column is here. It was not in the original data. The reason that we did this is that we are adding something so that we can have the concept of bias, or the concept of the y-intercept that we had before in our predictor. So if you remember before, the way it worked with 2 variables was that you would take an x, you would multiply it by a slope and add a constant value like a y-intercept, and then you would actually get the predicted value. In this case, you're taking x as a matrix, you're going to be multiplying it by w, that's like the slope for the most part, and you're going to be getting the predicted values of y. But this column, this set of 1s, always gets multiplied by this first element, w0. For example, 1 times w0 plus 25 times w1 plus 3 times w2 plus 50 times w3. That's how you would do a vector multiplication, or even a matrix multiplication. And so the 1 is always being multiplied by w0. And what you'll see is that w0 then turns out to be this idea of the y-intercept, or the idea of the bias that the model has to start with for creating the prediction. Okay, so what we need to do now is basically be able to calculate the best possible W. After that, as I said, we'll be able to take any row, multiply it by the same W, and be able to get a predicted value of Y. So we'd like to just continue on with this example. Now that we've got X, W, and Y in the right format, X is a matrix, W is another matrix, and Y is the output matrix. Our goal is to be able to have a predictor or an estimate for Y for new values of X that we've never seen. In order to do this, we are going to need to be able to calculate a W based on the values of X and values of Y that we already have. When we do this, when we calculate that W, you could say that we are basically training or learning from the data that we already have in order to make this predictor. Now, just as an example so that it's clear, we could take any row, once we know W, we could take any row, for example, the second one, 123, 260, we should be able to multiply it by W. And so 1 times W0 plus 23 times W1, 2 times W2, and 60 times W3. And when we add, when we basically take that dot product, we should get a number that's close to 580. If we have a good predictor of W, it would give us a value that's close to 580. So in that way, W1 through W3 are like the coefficients that got multiplied by each of these feature variables that are in these columns, that are in the feature columns of X. Okay, so now the question is only, how is it that you calculate the best W? And the place that we're going to start with this is by looking at the error that it would get created. So you can think of it as, well, what would the error be? If we took X and multiply it by W, we have our predicted value of Y, and we can subtract away the actual value of Y and try to see what is the expected difference. Now, this is not as good because sometimes you have a positive value of Y and sometimes you a positive error and sometimes you have a negative error, and they might cancel each other out. So a better measure of error would be the square, to take the error and square it and then take the average. So in this kind of summation version of the same formula, but this time we're going to take W times X for the predicted value, subtract away Y, the actual value, and take the square before we take the average. And so we're basically looking at the mean square error as a measure of error. Now that we have the error, and we can do this in matrix form, which is what this top formula is, what we're going to do now is we're going to, and this is important to understand, what we're trying to do is find the W, which would give us the minimum error. And so this is really error as a function of W, and we're trying to minimize it. So if you were trying to find the minimum or the maximum of any other function, something that you might consider doing is taking the derivative. In the matrix form, we're basically going to do the same thing of taking the derivative and setting it equal to 0. So we're going to take the gradient with respect to W and get something that looks like this as the gradient and set it equal to 0. By setting it equal to 0, we can basically solve for the value W. And when you solve for the value W, so you'll see when you do this, it looks a little bit messy, but it's really not. And you just do a little bit of matrix multiplication and you can get this W by itself, move the X transpose and X times X to the other side. And so here you have a result for calculating, effectively calculating the optimal value of W. Now, it's possible that when you look at this, it might look messy, but it's actually an amazing result and it's very tractable. And one thing I'd like you to do is consider the dimensions of this because it's not as messy as it looks. So if you look at X transpose times X, let's look at these one at a time. X transpose has this shape, which is, it's very wide, N is a large number, and D, the number of columns, that's a small number. So that has a shape that looks like that, and X has a shape, as you know, it's a deep table and it's very long, and the dimensions is relatively narrow. When you multiply those two together, what you actually get, even though this is a very large matrix with another very large matrix, you get something that's pretty compact. It's actually just D by D, meaning if you had 5 features in the X matrix, then this would be a matrix that's only 5 by 5. And then when you take the inverse of it, which you need to do in the original formula, then you would see that's also the same thing, d by d, or 5 by 5 in the example. If you then take that and multiply it by x transpose and y, what you'll see is that you're multiplying it by a d by n matrix and an n by m matrix. And these also basically collapse the whole size down to only something that's d by m. D is, remember, the number of features in the X matrix. M is the number of outputs that you are expecting to have. So again, if you had 5 features in your X matrix, like age and height and income level, and you had 3 outputs like credit score and frequency of visits to the business, and one more, then 5 by 3 would, then your matrix would literally be only 5 rows deep and 3 columns wide. And so once you have that D by M matrix, that's what W actually is. And then you can take any set of data that you've never seen before, even in matrix format, multiply it by that W, and you'll get another matrix of Y. So let me show you the same thing now in code format. This is an example in Numpy. Note that we took the exact data, the X's, 25, 3, 50, those are the same data that was in the table. We also still kept the ones that were the first column, as in the example, and we have Y, a vector with the different credit scores. And calculating W is simply just executing the formula. So the formula we just showed you in terms of matrix multiplications, and what you get is W with 3 coefficients and 1 W0, which is like the bias term. So think of it this way, which is that everyone's credit score turns out to have a bias or a base of 426 points. Then for every year you are older, then you will lose negative 60, then you'll lose 16 points on your credit score. And for every year that you've worked with the same employer, with the current employer, you gain 149 credit points. And for every extra $1,000 that you make, you gain 3.7 extra points on the credit score. Now, is this this is not a great formula for a credit score. It's just what comes out of this particular value of X and Y, but it does illustrate how W is calculated, and from a code point of view, how it can be done with actually very little code in NumPy. Now I want to bring you back to this slide, which we looked at in part 1. So we've seen this example before. What it shows is that that we can use the same library function with X. X can be, one variable, or X can be a vector like we did before with 1 input and 1 output, but X can also be a matrix, and it can have multiple columns of different features. Y can be a matrix that can have multiple columns of different outputs. And the code to use this library with multiple inputs and multiple outputs is otherwise the same. It's identical. And so it's a good example that all of the details, they've been done within the library function, 2-3 lines of code, all of that has been taken care of for you. But in addition, what this module explains is what is underneath this code when those predictions are being done for you. So this concludes the linear regression module. It also gives you an example of the machine learning framework that we're learning and that we're using. So in this framework, X is our input. It can be a single variable, it can be a vector, it can be a matrix. We generally put it into a function. We'll just call this function g of x, and we will get an output y. That would be our predicted value. We usually use some data to train so that we can learn g of x, and then later we can put in values of x that we haven't seen to get new predicted values. There are cases where we can just calculate the best parameters for g of x like we did with linear regression. And there's also cases where we can't calculate it, but we can take a good guess. And then we can see how close we are to a good predicted value of y. And if, and then we can, through iterations, try other versions of g kind of over and over after we look at the error, and then try another version of g, and then look at the error until g is getting closer and closer, and basically becomes good enough to be a good classifier. We would say that g of x has become close enough to that ideal or perfect function f of x, which would actually be the perfect predictor. And then once we have a version of g of x that is good enough, that has a small enough error when you use it, then of course we can use that in predicting any x that we haven't seen up till now. So we're going to see more of these types of predictors and classifiers in future sections of the course.